Afternoon class, this is Mr. Precella, and we're going to continue working that review for test 2. We had gotten to number 18, give all possible rational zeros for the polynomial f of x equals negative 2x to the fourth plus 2x cubed plus 5x squared plus 18. Let me switch over to my paper. Okay, remember to find possible rational zeros. I abbreviate that PRZ. They're equal to the positive or negative, and it's a fraction. On top, you have any factor of the constant term, factor of constant, and the denominator must be a factor of the leading coefficient. So let's write out the factors of the constant term. The constant term is 18. The factors of 18 are, let's see, there's 1 times 18, there's 2 times 9, and I think there's another pair, yes, 3 times 6. And we need the factors of the leading coefficient. Well, the leading coefficient is a negative 2, but this plus minus takes care of all of that. Just like negative 1 times a negative 18 gives us a positive 18, but we don't have to consider those because the plus minus takes into account all the possible sign changes. So I'll say the factors of negative, just the factors of 2, oh, that's nice, just 1 times 2. So we have to take every number up here, put it over 1. Then we take every number here and put it over what number? 2. That's right. So, and don't forget the plus minus. So we have a plus minus, we'll have a 1, plus minus 2, plus minus 3, plus minus 6, plus minus 9, and plus minus 18. We're putting them all over 1. You all following my pattern? Then we take every one of those factors of 18 and put them over 2. So we have 1, 2. So we're putting them all over 2 now. And we can clean all these up. For instance, every one of these that's over 1, we can just drop the 1. So I'm writing up my final answer now, cleaning up these fractions, simplifying the ones that I can. We'd have a positive or negative 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and a plus or minus 18. Coming down here, 1 over 2, that's 1/2. We don't already have it listed. But what about this one? 2 over 2. 2 over 2, isn't that 1? 2 divided by 2, so we already got that one. 3 divided by 2, do we have 3 divided by 2 listed already? No. So let's write it down. 6 divided by 2. That's 3, you're right, we already have 3. So we don't write that one down again. 9 divided by 2, 9/2. We don't already have it. Let's add it to our list. 18 divided by 2. That's 9, and 9's already listed. So here are all of the numbers that could possibly be rational zeros of the function. So if I asked you, could I plug in, say, 10 and make this thing equal 0? Your answer would be no, because 10 is not even a possible 0. Now, not all of these numbers are possible zeros. The largest number of zeros this function could have is 4. So these are the only numbers that could possibly be zeros, but we don't know exactly which ones are 0. We'd have to start either plugging, if we wanted to find out, we'd have to start plugging in to see if it equals 0, or use synthetic division to see if we get a remainder of 0. But all we're looking for are the numbers that could possibly be 0. So, switching back to the problem, it's a multiple choice. Now, the order in which they're written doesn't matter. I think it's B. 1, 1/2, 2, 3, 3 halves, 9, 6, 9, 18, 9 halves, yeah. Any questions there? Okay, number 19. Determine whether the function is 1 to 1. If it is, find a formula for its inverse. Well, when I look at this, I can tell it's 1 to 1. That means there's not going to be any repeated y values. We made a note when we were looking at these functions. How can we spot if something's 1 to 1? I'll write it right down here. And hold on. So remember I said not 1 to 1. If you're going to get if you're going to get repeated y values, that means your equation will probably contain even exponents like x squares or x to the 4th. And absolute values. So, looking back at the problem, there are no even exponents. There's no x squares or x to the 4ths. There's nothing that would take a negative quantity and change it positive. Also, there's no absolute value. So yes, this function is 1 to 1. We can convince ourselves of that. There's no actual work to show. And now they want us to find the inverse. So this is number 19. They want us to find the inverse. Okay. Let me move my page down. Hold on. There. Let's see, right there. Find the inverse. Remember, loosely speaking, an inverse swaps the x and y coordinates. That's what an inverse does. I don't even see a y here. I don't even see a y in this function. Remember, f of x is just a fancy way of saying what letter? Y, that's right. F of x is just a fancy way of saying y. So, you replace the y with an x equals 4 over, you replace the x with a y, and now we have to solve for y. Well, to solve for y, we need to get that y out of the denominator, so we're going to multiply both sides by the denominator, y plus 8. Multiply by y plus 8, and that'll give us, we have an equals 4 on the right side, and on the left side, distribute the x, y times x, that's xy, plus 8 times x. We're trying to solve for y, so what should we do next? I agree. We'll move the 8x. I see someone doing this little motion. Yes, we're going to move the 8x over to the right-hand side. So we have xy is equal to 4 minus 8x. And then x times y, what would undo that multiplication? I agree, division. So divided by x, divided by x. So the x's cancel out, leaving us y equals 4 minus 8x all over x. So my inverse function is 4 minus 8x divided by x. Although this step isn't really necessary, my lab already has the f inverse of x notation typed for you. All you have to type in is this stuff right here. So typing in the 4 minus 8x over x. You come over here. You have a fraction. On top is a 4 minus 8x. And on the bottom, it's just the variable x. Any questions? Number 20. Oh, I like this. This is one of those things that we can do without showing any work. If you remember a particular test that we use to determine whether the function's graph is 1-to-1. Is this function 1-to-1? What's the test we use? We use the vertical line test to decide if its function is a graph represents a function. Yeah, let me write that down. We use the vertical line test. The vertical line test tells us whether a graph is a function. Test if a graph is a function. And we use the horizontal line test. The horizontal line test is what we use to determine if a graph is 1-to-1. So, looking back at this function, can we draw a horizontal line so that it hits the graph in 2 spots? There are plenty of horizontal lines drawn. They're on that grid. Are they hitting the graph in 2 distinct spots? No. So yes, this thing is 1-to-1. If it's impossible to draw a horizontal line to hit the graph in 2 spots, then you're looking at a 1-to-1 function. Now, number 21. 21 will require some work. Okay. I want us to graph the exponential function y equals 4 to the x. So, remember what I suggested you do. To draw the graph of an exponential function, just plot some points. And I said that the integers from 3 to -3 would usually be sufficient, but if we use 3, 4 cubed, 4 times 4 times 4, that's 64. There's no way we're going to count up that many points. So I think I'll plug in a 2, 1, 0, -1, and -2. Plugging in a 2 for x, we get 4 squared. 4 squared, that's 16. 4 times 4. Plugging in a 1, 4 to the first power, that's 4. Plugging in a 0, 4 to the 0 power. No, it's not 0. What's 4 to the 0 power? 1. I agree. Remember we said a non-zero number to the 0 power is always defined to be 1. -1. 4 to the -1 power. That's not -4. A negative exponent is just a fancy way of expressing a fraction. Remember that's saying that's 1 over 4 to the first power. So 4 to the -1 is the same thing as 1/4. What about when we plug in the -2? 4 to the negative 2 power. 4 to the negative 2. That's 1 over 4 squared, which is 1/16. 1/16. So drawing our XY grid, remember we said we expect one side of the graph to be extremely steep, almost vertical. We expect the other side of the graph to be very flat, almost horizontal. Oh, right 2 up 16. I'm not going to bother plotting that order pair. 1, 4. Right 1 up 4, right there. And then the order pair 0, 1. I know where that is, right there. And then left 1 up 1/4. So left 1, there's negative 1. We're going up 1/4 of a unit. Imagine breaking that little increment right there into 4 equal segments. And at negative 2, we're just barely going up we're only going up 1/16 of a unit. I think to the naked eye it would look like the graph is touching the x-axis. But realize a positive number to any power will always be positive. There's no way you're going to get this to equal 0. So the graph will always have a little bit of space between the x-axis and the graph itself. So it looks like the left side is the side that's real flat. The right side is the side that's real steep. Now let's choose the graph, the matching graph. Oh, I don't even think we need to blow up these things. I think it's clearly A, isn't it? B, clearly not. C, no, that's not it. D, a line, I don't think so. The only one that's even close to it is response A. And now we're going to solve some exponential equations. The first method we had of solving exponential equations was to get a common base. Switching over to my paper. Two to the 2x minus 7 is equal to 16. Let me make sure I didn't miscopy that. 2 to the 2x minus, yes, okay. So, when we're using the same base method, we need the same base on both sides, and then you can drop the base and set the powers equal. Well, 2 is the base on the left side. 2 is a prime number. You don't want to change that 2. That means you better be able to write 16 as 2 to a power. So we have 2 to the 2x minus 7 on the left. 16. 2 to what power will give you 16? Don't say 8. 2 to the 4th power. 2 times 2 times 2 times 2 gives us 16. And once you have the same base on both sides, just drop the bases and set the exponents equal. So we dropped the 2's, set the powers equal, and it's a linear equation. We know how to solve that. Move the 7 over to give us 2x equals 11. I agree. 4 plus 7 gave me an 11. And then divide. Correct. Divide by 2 to give us x equals 11 over 2. For my final answer. Switching over, we have 11 over 2. Looking back at my work, any questions there? We wrote 16 with the base of 2. Once we have the same base on both sides, we drop the bases, set the powers equal. That is called the same base method of solving exponential equations. Number 23. It's another exponential equation. Oh, I should have mentioned, reminded you, I suppose, that an exponential equation means that the variable is up in the exponent position. Notice the variable is not on the base. We used to see things like x squared and x cubed. Here the x is part of the exponent. So number 23. Let's make sure I have this written down correctly. 81 to the 3x minus 6 is equal to 729 to the x plus 2. Yes. Switch to my paper. Move it down. This one will do. There, let me hide that. Okay. Well, when I see 81, I think of, if I'm going to try to write 81 as a power involving an exponent, oh, I better pull up my calculator. Give me a moment to pull up my calculator here on this thing. Let's see. Do I see it there? No, that's one of those things I need to do. I need to hold on. Here, I've got my calculator. And let's switch here. Oh, let me bring that thing back up. I said 81. When I think of 81, I think of 9 squared. 9 squared, we know that that's equal to 81. I wonder if we could write 729 as a power 9. Maybe 9 cubed. 9 times 9 times 9. Sure enough, that's 729. So, 81, I'll write as a 9 squared. We still have that exponent. 3x minus 6 up there equals 729. We can write as 9 cubed. We have that exponent of x plus 2. And now we need to remember, what do we do when we have a power raised to a power? There's a power rule of exponents. What do you do when you have a power raised to a power? You multiply. Yes, I agree. So, multiplying 2 by 3x minus 6, that's going to give me a 6x minus 12, I agree. On the right, multiply the 3 by the x plus 2 to get 3x plus 6, I agree. And now that we have the same base on both sides, no parentheses, we drop the base, drop the bases, set the exponents equal. 6x minus 12 is equal to 3x plus 6. I'd subtract 3x from both sides, 6x minus 3x. That would give me a 3x on the left side. And what will I have on the right? Move the constant term over there, and that's going to give me a, I agree, 18. 6 plus 12 is 18. Divide by 3 to give me x equals 6 for my final answer. Sometimes you have to change both sides, the base on both sides, to get a common base. Remember, a power raised to a power, you multiply. So going back to my lab, x is equal to 6. Number 24. This is a good one. Well, the previous one was a good question, good problem too, but still. Notice it has e's appearing as part of the base. Those e's are not variables. Those e's are representing the natural exponential, which is approximately 2.718, but you don't need to know the approximation for e to be able to get this problem done. E is an irrational number. If I have an e on one side and I'm going to get a common base, I better have an e on the other side, and I do. What I'm going to do is I'll write both sides with a base of e. I'm going to use e as my common base. Be thinking about your definition of negative exponent. How are we going to rewrite 1 over e as e to a power? I don't see a power on this e, so we assume down here there's an exponent. If you don't see an exponent, you assume a power of 1. And then using that definition of negative exponent, I think we said b to the negative n is the same thing as 1 over b to the positive n. So we're using it in reverse. 1 over e to the positive 1 is the same thing as e to the negative 1 power. Drop the 1 over, make the exponent negative. Applying that same logic here, 1 over e to the 8th power will be the same thing as e to the, I agree, negative 8. Drop the 1 over, change the sign on the exponent. And now you have powers raised to powers. So once again, powers raised to powers, you multiply. Negative 1 times negative x gives us a positive x. Multiply the negative 8 times x plus 4. That 8 looks strange. That is a negative 8. A negative 8. So you take negative 8 times x. Negative 8 times positive 4. Negative 8 times x is a negative 8x. Negative 8 times positive 4 is a negative 32. We have the same base on both sides, so we drop the base, set the exponents equal. We have to add 8x to both sides. 1x plus 8x gives me a 9x equals a negative 32. And then divide by 9 to give us the answer. X equals negative 32 ninths. We rewrote both of the bases as e to a power using negative exponents. Then we use the power rule, power to power, you multiply. Then we could drop the bases, set the exponents equal, and solve. So let me come over here and type in negative 32 over 9. And number 25, the last problem. Solve the exponential equation. The square root of 2 to the x plus 9 is equal to 16 to the x power. Here it is. Remember, I told you that there was something you needed to add to your bag of tricks with regards to radicals. When we're working with with exponentials or logarithms, when you run into a radical, you're going to want to rewrite it in terms of a rational exponent. Remember, we said the square root of b is the same thing as what exponent? 1/2. I agree. The square root of b is the same thing as b to the 1/2, and the nth root of b. In general, the nth root of b is the same thing as b to the 1 over n power. I agree. So We see that 2 there. We're going to write that as 2 to the 1/2 power. We still have that x plus 9 up there equals. Now, 2 is a prime number. You don't want to change 2. That means you better be able to write 16 as a power of 2. And I think we can. I think that we ran into that back on number 22, I think it was. 16 is the same thing as 2 to the 4th power. 16, just in case you don't believe me, 2 to the 4th power, sure enough, that's equal to 16. Powers raised to powers, we're going to have to multiply. So there's 2 and 2. 1/2 times x is 1/2 x plus, what's 1/2 times 9? 9 over 2, I agree. Only multiply the 1 times 9 is 9. 2 times that 9 is like a 9 over 1. 2 times 1 is 2. Over here, 4 times x gives us a 4x. We now have the same base on both sides, so we can drop the bases, set the exponents equal. 1/2 x plus 9/2 is equal to 4x. You know what I'd do? I'd get rid of the fraction. I'd go through multiplying by what to cancel out those denominators. It's just, the two fractions have the same denominator. What's the smallest? 2, I agree. We can multiply all the way across by 2. Multiply here by 2. Multiply here by 2. And multiply here by 2. I wrote it as a 2 over 1 since I'm multiplying a fraction, but over here 4x isn't a fraction, so I just wrote it as times 2. The 2's cancel here. What's that going to leave us with? Just 1x, I agree, plus the 2's cancel there. 9 over 1, just a 9, and here 4x times 2 gives me an 8x. Realize the real work in these exponential equations is just getting the same base on both sides, because once you've done that, setting the exponents equal, it falls out pretty quickly. I move that x over to give me 9 equals, I agree, 7x, 8x minus 1x gives me a 7x. And then I divide by 7 to give me x equals 9 over 7. For my final answer. Any questions there? We have our two properties involving rational exponents, how you rewrite a radical in terms of a rational exponent. Add that to your bag of tricks for exponentials and logarithmics. If you have a radical, write it as an exponent, and then we were able to write 16 as a power of 2 also. We multiplied using the power rule, and then we dropped the exponents. The bases, set the exponents equal, and I multiplied through by 2 to cancel out all the denominators. Final answer of 9/7. So 9 over 7. And look at that. We've done the whole assignment. I got the whole review. I got 100 on it. So I hope this helps y'all as you prepare for test 2. Bye-bye.